Consider the example, limit as xy goes to 0, 0 of the function x squared minus y squared over x squared plus y squared. Okay, so I'm not going to do it analytically. I'm not going to try to actually evaluate this limit using algebraic techniques or any of that. I'm just going to show you the graph of this function, and I'm going to show you why up here this is true. I'm going to find two paths, C1 and C2, along which the function's values tend to different numbers as we approach the same point, 0, 0. So let's do that. So I'm going to switch over here. And the first caveat that I'll mention is the usual one. This CalcPlot 3D is fantastic, but like all numerical plotters, it has trouble when we divide by very tiny numbers, or when we approach asymptotes or take square roots of tiny numbers. That is what's going to be happening here, right? So x squared plus y squared is in the denominator. And over here, as we get closer to the origin, we're dividing by 0. And it's even worse because the numerator is also becoming 0. So this poor computer program, we are forcing it to calculate something like 0 over 0. Obviously, that's not calculable, but the numerator is going to 0, the denominator is going to 0 as we approach the origin. So, Applet is understandably having trouble dealing with that. Nonetheless, let me pan around so you get a sense of what this surface looks like. It's actually quite nice and smooth, except for at the origin, right? So we are going to figure out what's going on there in a minute. Part of the way I'm going to do that is I'm going to ask you to keep your eye up here on the values of the function, okay? And so then I'm going to go over here and click on this, and then that's going to pop up for us. There you go. Over here, I can change the x and y values, and then keep your eye here for the z values, and then also glance over here every once in a while to see where the z value is on the function. So notice that I am going to leave y equals 0. So I'm just going to travel. I'm going to change x and leave y equals 0. So this is decreasing y. Y equals 0 is the xz plane. So you can see this blue dots. Basically, it's going to move around the top of the function this way and then this way. Once we get close to 0, this is where the limitations of the program, you'll see that'll be apparent. But okay, so I'm going to go here and I'm going to start at an x value that's way over there. So around x equals -2. You see on the right-hand side, as I move toward the origin, I'm just moving on the top edge of this function. And then if you're looking at the y values at the very top of the screen, they're all equal to 1. And then at x equals 0, this applet has a problem. It claims that the function's value is 0. But, the denominator is x squared plus y squared. When you substitute x and y both 0, you get 0. We can't divide by 0. So that's the issue that the applet is having. But anyway, at every other non-0 value for x and y, the y values, I think, are correct. And you can see at the top here, the y value remains 1. No matter what x value I am using, as long as I keep y equals 0. So now I'm doing something very similar, but instead I am going to set x equal to 0, and I'm going to travel along the changing y values. So I'm going to travel along the y-axis. So let me rotate the graph. I'm going to rotate the graph here so you can see the bottom part of what's going on. So now I'm traveling along. You see that bottom part that's kind of straight? That's what I'm going to, this bottom part here kind of straight, that's what I'm going to travel along as I change the y value. So now keep your eye on the function values at the top of the screen. They're all equal to -1. Again, there's an issue here when I get to 0, 0. The function's value is definitely not 0. It's undefined there. But for all the other values, the function's values are correct. They are -1. So what are we seeing? We're seeing that if I approach the origin along the y-axis, from the top and bottom directions, the function's values are -1. However, if I approach the origin 0, 0 along the x-axis, doesn't matter what direction I'm going in, the function's values are 1. So that tells me that I have an issue. If I go back to my gray takeaway box here, I have now found paths C1 and C2 along which if I try to evaluate the limit, then I get different function values, -1 and 1. So this limit does not exist. Okay. How would we show this analytically? How would we actually show this? And especially on a quiz or an exam, we don't have a technology with us. How would we figure this out? So let me do that by finishing up with this example. One of the best ways to do that, and I'll just mention quickly, this is a very similar function. It's not exactly the same, but I'll do this example first, and then we'll go back to the one we just did. One of the best ways to show that a limit does not exist, again, we're using this approach here of finding two paths where it does not yield the same function value, is to start with simple paths, right? So it's what I did in the applet right now. So how about first we try x equals 0. Okay. So let's try approaching the origin in this limit, which is, this is where we want to head to. Let's try approaching the origin along the line x equals 0. So if I do that, then I will still have to approach 0 for y. But here in the function, if I put x equals 0, I get 2y squared over y squared. And that is going to always be 2. Because remember, now we're back to single variable limits. That's why I wanted to review it at the beginning of the video. Y squared over y squared, this cancels so long as y is not equal to 0. But we're taking a limit. So y is never equal to 0 in the limit, right? We approach indefinitely in limits. So in fact, this limit is 2. Now we're going to try a different path. So what if we try approaching the origin in this limit, which is what we want to do, along the line y equals 0? Well, if I go back to here, well, I'm approaching along y equals 0. I still also need to make x equals 0 to make xy equal to 0, 0. If I go back to the function here and I set y equal to 0, I am calculating this limit. Similarly to before, right? X squared over x squared is 1, so long as x is not 0. It isn't, because we're calculating a limit. So I get 1. We can see here, if I were to draw this graphically, right? If this is the plane, then what have we shown in number 1? X equals 0 is the y-axis. So we have shown that, so here's the points we want to eventually find the limit at. We have shown that if I approach along the y-axis, the y value that I get, the limit that I get, is 2. And we also showed over here that if I approach along y equals 0, which is the x-axis, if I approach using these paths, the limit I get is 1. So these two L values are not equal, so we conclude that the limit does not exist. That limit does not exist. Okay, and as promised, let me go back then to the example we were just working on and do the same thing here. The same approach works here. So along x equals 0, we are, again, approaching the origin in this limit, so we would be left wanting y to approach 0. If I try x equals 0 here, I get negative y squared over y squared. There's that -1 that we were seeing in the applet. Along y equals 0, I still need to approach the origin, so I would need to make x go to 0. If I put in x equals 0, y equals 0 here, I get x squared over x squared. There's that 1 that we kept seeing from the function values in the applet. These two are not equal, so same conclusion from before, limit does not exist.